Hi, I'm Mose Sakashita. I'm a PhD student at Cornell University. I'd like to present our work SharedNeRF, leveraging photorealistic and view-dependent rendering for real-time and remote collaboration. This work was done with Bala, Nick, and Andy during my internship at Microsoft Research. In collaborative tasks involving physical artifacts, the ability to observe the task space in high fidelity from various viewpoints is important for conducting smooth interaction and collaboration. But sharing a physical object remotely is extremely challenging because people often fail to provide the perspective that the other person needs to see. We present SharedNeRF that leverages photorealistic NeRF rendering for remote collaboration, allowing a remote collaborator to change the viewpoints to look at the physical objects from different perspectives. The remote collaborator can also see the dynamic hand movements and gestures through point clouds and 3D avatar. As the local collaborator makes changes to the scene, the system can update NeRF representation on the fly. To achieve remote sharing of task space, previous work explores the methods of providing multiple camera views to a remote collaborator, such as showing them on multiple displays, using an auto-controlled camera, or saving snapshots of key moments. However, they can only offer limited perspectives of a shared object. Head-mounted cameras or handheld cameras are also often used in remote collaboration, but a viewpoint heavily relies on the local collaborator, who often fails to give the exact viewpoint that the other collaborator wants to see. In order to give a remote collaborator access to seamless viewpoints, other work uses spatial rendering techniques where a remote collaborator can freely change their viewpoints to look at shared objects. Point cloud or mesh rendering using RGB-D cameras enables real-time sharing of a task space, offering free viewpoints in 3D space, but often lacks necessary fidelity, introducing noise or missing meshes. Recent Neural Radiance Fields NeRF or Gaussian splatting provides high-fidelity, photorealistic, and view-dependent rendering of physical space, but its representation can be slow to update due to the training time. In our work, we explore the question of how we can leverage the complementary nature of NeRF and point cloud rendering for real-time and remote collaboration involving physical artifacts. Now, I'd like to present the key components of SharedNeRF. First, I'll talk about how the system captures a dataset to train a NeRF model on the fly, as collaborators work on physical artifacts remotely. To capture the dataset, the system uses OrbsLAM to track the poses of a head-mounted camera worn by a local collaborator. These poses and images are sent to a remote location and added to the dataset for training a NeRF model. Training NeRF only based on the first few frames and camera poses does not result in good NeRF representation because the dataset contains similar head poses. The system has to improve the quality of the NeRF model over time. To do that, the system optimizes the training dataset by maximizing the diversity of camera poses as the local collaborator moves their head around the task space. The technique described above can create a complete NeRF representation of a static scene in the shared space. But the shared space is not static, meaning collaborators often make changes to the scene, moving objects around or adding new items to the scene. Here, I'd like to talk about how the system updates NeRF when dynamic changes are being made in the scene. There are two main problems with the approach presented so far when the task space changes dynamically. First, moving hands and objects cause an inaccurate NeRF representation due to an inconsistent dataset. For example, in the dataset, some images might have one state of the scene, but other images may contain another state of the scene, resulting in the image that you see on the right. To avoid this, we have to detect moving objects or hands and stop adding images to the dataset. Another problem is that the NeRF representation is static even when changes are made. To keep the NeRF updated, the system needs to detect scene changes and train the NeRF model with a new dataset. A stationary camera is used to calculate optical flow for detecting dynamic movements or changes occurring in the scene. For motion detection, we use optical flow between the current frame and previous frame. For detecting scene changes, we use the frames right before and after the motion is detected. This detection guides the system on when to add new images to the dataset or when to update the NeRF model to the new state of the scene, replacing the dataset. Using this technique, as the local user makes changes to the scene, the system can update the NeRF representation accordingly. The user can repeat the alternations to the scene, which is also reflected on the NeRF model for sharing the new state with the remote collaborator. Although the system now updates the NeRF model upon scene changes, the update rate of NeRF is still slow to keep tracking what's going on with the moving objects and hands in the scene. To share dynamic elements of the task space with a collaborator, we seek to leverage the real-time point cloud rendering for dynamic objects and NeRF rendering for static objects. Here's the visualization of blending both NeRF and point cloud using naive superimposition with Z-buffer. You can see that this blended view eliminates the black patches that you often see in point clouds by showing NeRF. It also visualizes the moving hands as point clouds, accurately occluded by objects rendered by NeRF. However, relying on the Z-buffer alone can cause an issue where moving an object results in duplication being rendered by both NeRF and point clouds. To solve this issue, we need to create a mask to show only dynamic parts through point clouds. To create such a mask, we use color and depth images from NeRF and point clouds by subtracting them and then binalizing them with a certain threshold. These masks help determine which pixels should be rendered through NeRF or point clouds. As the color mask and depth mask have their own strengths and weaknesses, our shader uses a weighted average of the color and depth masks to enhance the blended rendering. It's also important for the remote collaborator to be able to understand the social cues of the local collaborator, such as hand gestures or where they are looking. The system achieves this by showing moving hands with point clouds and head rotations through a 3D model. Here's a demo of using SharedNeRF in flower arrangement. The remote collaborator can examine the flower design while adjusting their viewpoints for better observation. They can also see the real-time hand gestures through the point clouds, as well as the local user's attention through their 3D avatar. After the remote collaborator specifies a flower, the local collaborator adds the flower to the design, allowing the remote user to see the dynamic elements in real time. The collaborators can review the final design, looking at different elements of the flower. The system is also useful for computer inspection, where the remote collaborator examines the computer setup to identify an issue. They can see the real-time movement as the local collaborator connects the cable to the GPU. The remote collaborator can review the new configuration, taking a close look, or stepping back to have a broader perspective. We conducted a user study with the objective to investigate the efficacy of SharedNeRF in remote collaboration. We recruited 7 participants to have them use our system in flower arrangement tasks. We compared the SharedNeRF condition with the first-person video condition, where they were shown a video from head-mounted camera, as well as the point cloud condition. Based on our qualitative feedback analysis, we found that all the participants commented on the independent control over viewpoints using SharedNeRF. One participant noted that they appreciate having independent control on the view they have. Another participant commented that they can accomplish a micro goal like zooming in to look at the details without having to interrupt the other collaborator on the other side. They also shared their thoughts on visual fidelity of SharedNeRF, saying that it did a great job of letting me observe such details, or it is easier to see the structure than the point cloud condition. But there was also a problem with clarity. One participant stated that some angles are better than other angles due to the lack of the data collected around those areas. Regarding the visibility of the dynamic elements in the scene, a participant noted that having the live updates through point clouds made it easier for them to figure out what was going on. Another participant also stated that they could see the local person's hands, head, and movements. However, there was some negative feedback as well. For example, one participant said that they couldn't see the moving parts as clearly as static objects rendered by NeRF. Another participant also mentioned that it wasn't easy to see changes on moving objects as quickly as the video condition. In summary, we present the design of SharedNeRF, leveraging the strengths of NeRF and point clouds for facilitating remote collaboration. We also demonstrate the on-the-fly NeRF training and updating technique. The system blends photorealistic NeRF for static elements and point clouds for dynamic elements using a mask. The user study investigates the efficacy of SharedNeRF, with the results suggesting that users perceive the benefits of the system in terms of the visual fidelity and dynamic elements of point cloud. Finally, I'd like to thank all the amazing collaborators at the MSR for making the project possible. Thank you for listening.